Hello everyone, welcome to watch this video. This is Parka Yi, and I'm working with another groupmate with this project, Lou Zhihao. This video is presenting you with our project topic, Generating Piano Music with Generative Adversarial Network, GAN. If you don't have any music background, can you create your own piano music in just a few seconds?
Yes, you can. With machine learning and artificial intelligence, computers are getting creative. They can now generate.
Then what is GAN? How does it work? GAN is Generative Adversarial Network, and it was firstly mentioned by Ian Goodfellow in 2014. GAN is a method of unsupervised learning. It lets two models to be trained together in a zero-sum game, adversarial, until the discriminator model is fooled about half the time, meaning the generator is generating plausible examples. Some examples of GAN's applications are improving cybersecurity, improving healthcare, generating animation models, editing photographs, and image translation. Then we have a look at the model structures. GAN is composed of two neural network models, a generator and a discriminator. The generator learns to develop new samples, whereas the discriminator learns to differentiate the generated examples from the real ones. These two models work together to train the GAN to generate and distinguish new plausible samples from the existing datasets. After that, we apply GAN to generate a new piano song in our project. We looked for 120 sets of reformatted MIDI piano music from Kaggle, then turned each segment datasets into a 128 by 128 two-dimensional matrix. Flatten all the matrices to be the input for the GAN. Then we make all the output tempo to 120 beats per second.
For our model design, we will employ a model structure that looks like this. As a starter, we will have a generator, where the generator accepts a latent variable of size 100 and expand it to the certain size. We shape this input to a tensor of 3 dimensions and use transposed convolutional neural layer to expand the dimension to 120 and 128. We can then use convolution layer to convert the output into one channel as our generation. For the discriminator, we try to make it simple. We'll use the convolutional neural layer and then followed by a leaky ReLU and dropout layer. We repeat this plot for 2 times, then we flatten the result and pass it into a dense layer of 1 neuron with the activation function of sigma 1 function. The GAN network can then be created by joining these two networks. The training procedure is then like this. First, we use the generator to generate a list of MIDI for each batch. We mix this data with real input to train the discriminator. Next, we freezes the layers of discriminator to train the whole network of GAN to update the weights of the generator. We train this network for 10 epochs with 100 batches to make sure the generator converges. We train the number of epoch generator based on the accuracy of the discriminator. For each of the epoch, the accuracy changes as below. We can see that at epoch 9, the generative adversarial network considered as well trained because the discriminator can only guess 50% of the input as real. As a result, we want to show one of the music that is generated. So this is the music where the latent variable changes from -1 to 1. So I'll pass my time to Justin.
Finally, our conclusion is that GAN can not only be applied in these 5 applications, but also can learn the piano rhythm to create a completely novel and beautiful piano music. This is the end of our presentation. Thank you for your attention.